So here's 9 and 11 from this week's assignment. The big idea being that electrons can only exist at these different energy levels. That's kind of Bohr's model for the atom. So if an electron has enough energy to jump up here, and that's as high as it goes between D and E, it still needs to settle somewhere at D, C, B, or fall all the way back down to A. But they can only exist on those energy levels. They can't exist in between. So that's kind of the big idea here. So number 9 says an electron with 5 eeV of energy collides with an electron in the ground state, and we want to find what happens as the electron moves to the ground. So the different energy levels that electron can take. So if it has 5, I'll use a different color. So if this electron has 5 electron volts of energy, that means that it can get all the way up here, but it can't get up to D. So this electron is going to be up here and then have to fall back down onto that level C. That's where that electron is going to be. From there, that electron can undergo a couple of energy changes as it goes back to ground. It can go all the way down to A. It can also go down to B, or when it's on B, it can go down to A. So it can really undergo those energy changes. So it can go from C to A, it can go from C to B, or it can go from B to A. Now the change in energy is just the difference between those energy levels. So 5.52 and 10.38. So as it goes from C to A, this change is 4.86 electron volts. As it goes from C to B, that's 0.24 electron volts. And as it goes from B to A, 10.38, that's 4.64 electron volts. To calculate wavelength then, we have our energy is equal to hc over lambda. I'm going to use the 4.14 times 10 to the negative 15 because I'm dealing with electron volts. So 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by 4.86 gives me, I guess I can write this, nanometers is probably easier to see, 256 nanometers. And I would do the same calculations for B and C as well. Finding wavelength by taking Planck's constant, the 4.141, times C divided by the energy change, and that's the energy of the photon that's emitted. When we classify it, so 256 nanometers, if you think of visible, that's 750 is red, 350 is violet, so this is outside of that. So this would be UV when we look at it. Okay, and then number 11. So number 11 says a photon will be absorbed if a transition exists that is exactly the same amount of energy as that photon. So it's saying this photon's coming in. So here's a photon. It has 0.22 electron volts of energy, and it's completely absorbed. So it's asking where the atom is, or what the energy of the atom is if it actually absorbs that photon. So we're looking at an energy change of 0.22 electron volts. So if that photon hits something at this energy level, right, it will move up to this energy level and that photon will be absorbed. because the difference between C and B is 0.22. Oh, I screwed that up here. So this is 0.22 electron volts. So that corresponds to that change. The big idea is that electrons can only exist at these different energy levels. If something comes in, like say with 4 MeV, and that electron jumps up here, well, that electron is going to fall back down to A because it doesn't have enough energy to get to B. So we can't have electrons in these in-between spaces. Electrons can only exist on those lines, kind of like the shelves in this week's assignment that you're going to be talking about.